Hello, I'm Maria Tosopoulou, and I'm a PhD student in the Department of Surveying Engineering of the Aristotle University of Thessaloniki. At the moment, I'm an early-stage researcher in the Laboratory of Photogrammetry and Remote Sensing in the same department. My areas of expertise include photogrammetry, remote sensing, GIS, and cartography. As an early-stage researcher, I'm participating in the MAIL project, identifying marginal lands in Europe and strengthening their contribution potentialities in a CO2 sequestration strategy. I have worked on task 2.3 under the work package 2 of the project, focusing on the development of a methodology for identifying marginal lands. My work included the refinement of the proposed methodology, its implementation to different test sites across Europe, and the automation of the whole procedure. In this video, we are going to present the first phase of the methodology, and more specifically, how we can use readily available geospatial data to identify the so-called hard layers of the methodology. These layers are referring to areas that, based on their spatial characteristics, cannot consider marginal lands and thus are excluded from further analysis.
Before moving on, the main question is what is a hard layer in the MAIL project? Hard layers are representing areas that, according to the proposed methodology of the MAIL project and the definition of marginal lands, are not considered marginal lands. These areas are urban areas, protected sites, areas covered with water or snow, forest areas, peat bogs, marshes, and croplands. In general, according to the definition of marginal lands, which is adopted in the MAIL project, marginal lands are lands with significant either environmental or socio-economic constraints and with potential to impact national accounting for carbon stock. Therefore, the above land use categories are valuable areas that cannot consider marginal lands and thus are excluded from further analysis. On the other hand, examples of marginal lands are grasslands, abandoned croplands, or other lands, excluding from them those with social economic activity, environmental protection, or other legislative restrictions. To identify these areas, several land use land cover geospatial datasets were utilized. In the table, you can see each one of these datasets and their corresponding use to implement the proposed methodology. Namely, the Sentinel-2 Global Land Cover 2017 product was used as a reference to mask all the land use categories that are not considered marginal lands, including water areas, areas covered permanently with snow, peat bogs, and marshes. In addition, the Global Forest Change products of the University of Maryland and the High-Resolution Tree Cover Density product of Copernicus Land Monitoring Service were used to define and exclude the forest areas. Moving on, the protected areas were excluded using a combination of the nationally designated areas and protected sites polygon and the Natura 2000 sites. In cases that the land use category we needed to exclude was described in different datasets, these datasets were combined using the majority value. For example, the Sentinel-2 Global Land Cover 2017 product, the Corinne Land Cover product, and the Perviousness high-resolution layer were combined to exclude artificial areas, croplands, and all changed areas. Changed areas are referring to land use categories that were changed from potential marginal land use to a land use category that is not considered marginal land. Focusing on each dataset, the Sentinel-2 Global Land Cover Map of Europe is a land cover dataset resulting from Sentinel-2 satellite imagery with a spatial resolution of 10 meters. In this dataset, 13 land cover classes are identified in total, and the data are freely available at the CREODIAS repository. The Global Forest Cover and the corresponding Global Forest Cover Loss datasets are raster layers representing the global forest extent of 2000 and its corresponding changes between 2000 and 2018. These datasets are provided by the University of Maryland for free and are also available in the Google Earth Engine platform. Forest areas are also included in the high-resolution tree cover density layer of Copernicus Land Monitoring Service. These products are resulting from Sentinel-2 imagery with a spatial resolution of 20 meters. The layers are available from 2012 to 2018. Moving on, the protected areas datasets are referring to vector files representing all the protected sites around Europe. The datasets are available at the European Environmental Agency data repository in spatial and tabular information. The Corinne Land Cover Inventory provided by the Copernicus Monitoring Service is a widely used dataset in remote sensing applications. The product includes land cover maps and the corresponding changes maps with a minimum mapping unit of 25 hectares. The land use categories are organized into 44 classes, and the product is available at no cost in the Land Copernicus repository. Finally, for the definition of urban areas, the imperviousness density layer was also utilized. These products are representing the percentage and change of soil sealing, and along with the other land cover products of the Copernicus Monitoring Service, are available with a 10-meter spatial resolution for the status map of 2018 and a 20-meter spatial resolution for the corresponding maps of 2006 and 2015. In the first phase of the proposed methodology, we tested and evaluated different combinations of all the above datasets to delineate each land use land cover category. Considering the spatial resolution of each dataset, and before applying any calculations, all the available layers are exampled according to the Sentinel-2 Global Land Cover layer, which is used as a reference layer, and all data are reprojected into the European grid projection. Different geoprocessing tools including fuzzy overlay, weighted overlay, majority value, and more were utilized to combine these layers. In order to handle each dataset, all data were transformed into binary rasters where pixel values equal to 0 are indicating no data and pixel values equal to 1 are referring to the values of each land use category. For instance, the raster layer representing forest areas is a binary raster where 0 values are indicating non-forest areas and pixel values equal to 1 are for forest areas. This flowchart illustrates the overall approach of the proposed methodology. As you can see, the computation workflows for each land use category were developed independently to ensure that in case of possible changes, the structure of the workflows for the production of each remaining intermediate layer won't be affected. So in this approach of hard thresholds, 6 individual workflows were developed, while an additional finer workflow combines all of the resulting intermediate layers to calculate the layer of marginal land hard, containing all the remaining land use land cover classes that meet the requirements of the definition of marginal lands. For instance, to delineate forest areas, we start by combining all the different datasets that can provide this information. The scope of this workflow is to define forest extent for the reference year of 2018, that is, the intermediate layer Forest 18. Starting from the high-resolution tree cover density dataset, we extract all areas with tree cover density greater than 30%, taking into account the definition of forest according to FAO. The produced raster layer is reclassified into 2 classes, representing forest and non-forest areas respectively. The final intermediate layer is the forest extent of 2015 according to the high-resolution tree cover density dataset. The same procedure applies to the second available forest dataset, the Global Forest Change dataset, representing forest extent of 2000 and the corresponding changes between 2000 and 2015. The 2 intermediate layers, Forest 2000 and Loss 2015, are further combined to define forest extent of 2015 according to this dataset. To delineate the final layer of forest extent 2015, a weighted overlay is applied to combine these 2 different forest datasets, taking into account the comparative validation of both products, which indicated that the high-resolution tree cover density layer represents forest more accurately. The final intermediate layer represents now the forest extent for the reference year of 2015. Finally, to delineate the forest extent of 2018, the produced layer is combined with the corresponding loss of 2018. In the final step, all the layers that are representing the extent of each land use category are combined to identify the final marginal land hard layer representing all potential marginal lands after the implementation of the hard thresholds approach of the methodology. According to this approach, all the previously produced intermediate layers that include land uses that cannot be marginal lands are now combined with the Sentinel-2 Global Land Cover base map. The final ML hard is a raster dataset including all remaining classes that could represent marginal lands. The section is completed with the implementation of an example in the QGIS software following this presentation. Namely, the example focuses on the calculation of the hard layer of imperviousness for the delineation of urban areas. Thank you for your attention.